So here's another problem involving a joint density. Pretty much the first thing I'm going to do when I'm approaching a problem here with a joint density is I'm going to draw a picture almost before I've even finished reading the problem, right? So I'm even going to, let's do that. Let's go ahead and draw a picture right now, right? So I have my picture, I have my x and y axes here. I know that x goes from -2 to +2. I know that y is less than the absolute value of x and is bigger than 0. So if I graph the absolute value of x, which, by the way, if x is negative, the absolute value of x is negative x, right? This, if you sort of cover up the right-hand side of your picture, you see that that's the graph of y equals negative x. The absolute value is positive x when when x is positive, and y is less than the absolute value of x. So I'm interested in these two shaded regions below my picture. Note that my picture is symmetric. Right, because x went from -2 to 2, my two shaded regions are exactly mirror images of each other, and that the density, when you look at the mirror image points from your density, my density is just the absolute value of x term. My density is also symmetric. So when I find my expected value of y, I could do the integral, a double integral over each region, or I could save myself some time and just say the expected value of x of y is 2 times the double integral of, I'll do the right-hand region because I find it slightly simpler. X goes from 0 to 2, y goes from 0 to x, and then I have y times f of x. I have y times the joint density. So I have y times 3/16 x times y cubed dy dx. Right? This 2 out in front, there I'm using symmetry. When you have problems with absolute values, it's often, but not always the case, that you can do little shortcuts like this to use some sort of symmetry. Likewise, a lot of times when you have squares going on, you can use some symmetry there as well. All right, so let's pull our constant out in front and do some rearranging. So I have 3/8 integral from 0 to 2 of the integral from 0 to x of x times y to the 4th dy dx. The integral of y to the 4th is very easy. It's just y to the 5th over 5. So I have x times y to the 5th over 5, evaluating y from 0 to x, and then I'll do an integral from dx, right? So that gives me 3/8 times the integral from 0 to 2 of x to the 6th over 5 dx. The integral of x to the 6th is x to the 7th, so I still there at 5 times 7. I'm evaluating from 0 to 2, so now I just plug into my calculator, and I get 1.4. Well, actually I get 1.37, but my answers are rounded off to near a cent, so I get 1.4.